Welcome to the Explainer. When you look at the ground beneath your feet, it's easy to think water just kind of sits there. But actually, there's this entirely unseen, dynamic physics engine at play. An invisible energy system dictating exactly how soil grabs onto moisture and when it decides to let it go.
So here's how we're going to break this down today. We'll start with the raw energy of soil water. Look at the actual forces pulling it around, get into suction, tension, and the PF concept, map out some soil moisture constants, and finally, wrap up with exactly how we measure all of this in the real world.
All right, kicking things off with the energy of soil water. We really need to zoom in here to the microscopic level. Down there, soil water acts like a physical body holding on to specific quantities of kinetic and potential energy.
And the absolute core concept driving all of this? Free energy. Basically, free energy is a measure of water's escaping tendency. Think of it like this. Water is constantly trying to escape, always wanting to move from a state of higher free energy down to a lower one. It's exactly why water naturally moves from saturated wet soils right into dry soils. It's just following that energy gradient.
Which brings us to soil water potential. Technically, this is the amount of work required to change soil water back into pure water at a reference state working against all the force fields acting on it. Now, the crucial takeaway here is that if the total potential of water is constant across the soil, we hit a static equilibrium. No net force, no movement. But the second that potential isn't zero, a microscopic tug-of-war begins and the water starts moving.
Okay, moving right into the forces pulling that water. Let's meet the four main competitors engaged in this endless battle over water's escaping tendency.
Total water potential is basically the sum of a few distinct competing forces. You've got gravitational potential, pulling the water straight down, then pressure potential, pushing it, driven by the weight of the water column, or even gas pressure. But the soil itself, it's constantly fighting back, desperately trying to hold onto that moisture using metric and osmotic forces.
Let's look closer at how the soil physically grips the water. That's your matrix potential, and it's driven entirely by adhesion and capillarity. It's actually fascinating. When water is adsorbed by those soil solids, it loses energy. We call this energy loss the heat of wetting. Because the soil is literally pulling and holding the water, matrix potential is always a negative value. The free energy is reduced.
Next up is osmotic potential. You see, water molecules are dipolar, meaning they naturally attach themselves to ions and solutes hanging out in the soil. This is exactly why excess salt is such a massive problem for agriculture. The osmotic potential traps the water so incredibly tight to those soluble salts that plant roots simply don't have the strength to pull it away. The water's there, but the plants can't touch it.
Now for suction, tension, and the PF concept. We know these potentials are negative. But how do we actually calculate this tug of war without drowning in clunky negative numbers?
Well, dealing with inherently negative metric and osmotic potentials can get pretty frustrating. So back in 1935, a scientist named Schofield proposed a workaround called PF. Basically, PF is an exponential function of that free energy difference. Specifically, it's the base 10 logarithm of the numerical value of the negative pressure of soil moisture expressed as the height of a water column in centimeters. It just makes the math way cleaner to work with.
And in the real world, a specific pH range from 2.8 to 4.4 matters immensely. Why? Because it represents the absolute optimal moisture window for tilling medium-textured soils. If you try to till outside of this sweet spot, you are going to ruin the soil structure. You'll either end up puddling wet dirt into a mess or shattering dry, highly cohesive soil into giant clods and useless powder.
Moving on to soil moisture constants. To really put this to practical use, we establish specific reference points to track exactly when water gets stuck or released in the dirt.
As we track the water potential dropping, you can really see how extreme it gets as soil dries out. When the soil is completely saturated, the potential is basically zero. But as it drains down to field capacity, it drops to -1/3 of a bar. Hit the wilting coefficient, and we plummet down to -15 bars. And from there, it just keeps dropping exponentially.
Just to really drive home how intense these forces are, think about oven-dry soil. Even when soil seems completely bone dry, it is still holding on to microscopic traces of moisture with a staggering 10,000 bars of potential. That is an immense amount of physical force.
This brings up a really crucial contrast for agriculture. Field capacity is your sweet spot.
That's when heavy rain has drained out of the larger macropores, but the tiny micropores are still filled with water that's readily available for plants to drink. On the flip side, you have the wilting point. This is the exact moisture level where the soil holds the water so tightly that the plant simply can't extract it fast enough to replace what it's losing through transpiration. Once it hits that point, the plant shows wilting symptoms it just cannot recover from.
Finally, let's talk about measuring soil moisture. To wrap up this explainer, we're going to look at the actual physical and electrical tools humans have engineered to measure these entirely invisible forces.
The most standard approach is the gravimetric method. It's a very tangible physical process. You collect a fresh soil sample from the field and weigh it. Then you bake it in an oven at 105 to 110 degrees Celsius overnight and weigh it again. The difference in weight? That's your water content. It's straightforward, though you do have to keep in mind that the oxidation of organic matter while baking can sometimes throw off your results.
But we've moved way beyond just weighing dirt. We have some incredibly advanced tools now. For instance, we use electrical resistance, which uses platinum electrodes embedded right into gypsum blocks, read by a modified wheatstone bridge. We also use tensiometers with porous ceramic cups, though those top out around -0.8 bars. Need to measure higher tensions? We switch to psychrometers to estimate vapor potential, or use laboratory pressure membrane apparatuses that can handle tension values up to a massive 100 bars.
And I'm going to leave you with this wild thought. To figure out how wet the dirt is, we literally shoot fast-moving neutrons into the ground. Seriously. In the neutron scattering method, we use radioactive sources like americium and beryllium to fire fast neutrons directly into the soil. As they collide with the hydrogen atoms in the water molecules, they slow down. A gas detector then catches those slow neutrons and uses them to count the water content. So the next time you look at the ground, just remember the sheer length science will go to just to measure the escaping tendency of water.